Okay, the fundamental theorem of calculus. Sounds serious, right? And it is serious because we will use it a lot, but it's not such a big deal. And it will link in particular the two things that we have seen. Let's quickly review what we have seen. We have talked about the notion of area, and the correct way to say it is area with sign, because we saw these things could be negative. And how is that defined? Well, you take the limit of a difference quotient, sorry, not the limit, that's the derivatives. You take the limit of these sums here. Sorry, that's not a dx, that's a delta x. And this was strips that were between A and B. Okay, the picture was this, right? We have an F here, here is A, here is B, here is X, here is one of these strips that we flatten, and the width of this strip is delta X. Oh, sorry, I cannot go in that area there, delta X. And the height of this, on the height of this strip, of course, that is f of x. Okay, just go back, look at the previous video. That's the area. Then we have talked about antiderivatives. Okay, and so I'm going to give you the formula, and then we will, at the end, I will explain where does the formula come from. And it has to do now with antiderivatives. So remember, the notation of this was, so this is the notation, right? AB fx dx. Now, we had also noted the notion of antiderivatives. That was kind of the opposite of derivatives. Let's playing Jeopardy with derivatives, right? The game show. And the derivative of fx dx would be denoted like that. So this we call a definite integral. And this we call an indefinite integral. And the only difference being that there are no endpoints. And why do we do that? Well, here is the thing. Suppose we have found an antiderivative. And let's call it capital F. Okay, because it's a new function, so I'll give it a new name, but it's custom to call it a capital F. And so this is now the formula, the fundamental theorem of calculus. There are actually two versions, two parts, but I'm only going to do the part that matters for us. So I'm calling that the fundamental theorem of calculus. And I don't remember, each book does call part one something else and part two the other guy, but what I'm calling here, what is that? Well, it says that if you want to calculate this, if f is a continuous function on the interval ab. Now, this means just for us that f is defined on ab. It means more, but for us it doesn't never happen. So it's for a higher honor course, calculus course, so that we would look into what this condition actually means. But for us it's just any good old function that is defined on ab. Okay, so if we now calculate this, if we want to calculate this thing, what do? Well, first of all, you calculate this antiderivative, which we called f. So f is an antiderivative of little f. And then you just plug in the endpoints, fb, fa, and you subtract. Not add, but subtract. And the order, therefore, is important. Notice it's the top endpoint that comes first, and the bottom endpoint goes second. Okay? And it's sometimes easier to write this way, so that we keep the same order, vertical order here, A and B, but notice that instead of an elongated integral sign, we have now a straight line, which is no longer in front, it's now in the back. It's kind of, we did our work. It's like making this symbol go through this function, and you get at the end there. Why do we do this? Let me give you immediately an example. Here's the first calculation of an area, which is, as I said, not trivial at all. To calculate this area, before calculus was invented, it was very difficult. And here it is. It's very simple. Let's take the parabola. So y is x squared, so the formula is x squared. And I want to calculate here, let's just call this 1 from 0 to 1. And so we are talking about the region bounded by this curve, right? So this is this part. Okay, again, I went out of my lines, but that's not important. So let's write down first, how does it, the formula, what's the area? How does it look like? What's the rotation? Well, it goes from 0 to 1. Now what is f? X squared. Is at the end of my notation? Don't forget, there's always this, don't forget, there's a dx there, right? Okay, good. Now what do we need to do? This says, find an antiderivative of this function. So in other words, do the same integral, but now without endpoints. Okay? Now this one I just explained in the previous video, that's the power rule, x cubed over 3 plus a constant. It says antiderivative. Which constant should I use? Well, since it doesn't matter, you can use whatever you want. So take 0, right? Okay. So I want to write this now in here, right? I want to write this formula. It's x cubed between 0 and 1. So you know, see that what is nicer to write it this way is with these bars here, because this means what? This is the easy part, right? Here it means you plug in 1 into x cubed, that's 1 cube. You plug in 0 into x cubed, that's 0 cubed, and subtract. Of course, that is just 1 minus 0, that is 1. So kind of weird, right? That the area underneath this parabola is actually 1 here. Oh, sorry. What I was saying, I knew it was not right. Because that would be 1, right? I forgot my over 3 here. Right? As x cubed over 3 is my antiderivative. So I have to plug in 1 on here and this, so I get 1/3. So the area is actually 1/3. Even weirder, right? That is 1/3. Okay. And so we can now, with this, you have all of a sudden a lot of areas you can calculate. And what it mainly does is the problem of area of definite integral becomes a problem of antiderivatives of indefinite integrals. So that's why it's called the fundamental theorem of calculus. It makes one problem into other problem. Now, antiderivatives is a hard problem, and that's why the rest of the next 2 weeks or most of the next 2 weeks are devoted to it. But once we know the antiderivatives, we can use that to calculate areas. And also we'll see later at the end of the course, we can use this to calculate other things like volumes and so as well. Okay. I don't want to say too much about it anymore. Again, I'll let you do a lot of problems. But I want to point out one thing here. Let's go back to this simplest example that I gave in the first video of a triangle. We know that the area of this triangle, I hope you still remember, that the area would be base times height divided by 2, that would be a half. Does this jive, does it fit with what we now have, our new method? Okay, so what do I need for that? What you need for this method is the equation of this, of what? Of this line. Okay, that's sometimes a little bit weird to find an equation of a line. I'm not going to think too much, let you think about it, but I'm saying it is 1 minus x. That's the equation of the line. It's slope minus 1 because it goes down, right? And it's 1 minus x. If you don't trust me, you can check it out for yourself. Calculate it yourself, the equation. You have 2 points, right? If you have 2 points, you can find the equation of the line. Okay, so in other words, our area, so this is what we call, let's call this the high school area, right? So perhaps it's not half, it's almost like 0.447449 something. Let's see, our area. We take the curve, we integrate, and what are the endpoints? 1 and 1? No. Always on the vertical x-axis here, from 0 to 1, right? From 0 to 1. Okay, I know, this is a sum rule. That is x and the derivative of 1. See, I'm not even doing that separate anymore. I do it in my head, right? And then the power rule, add 1 to the exponent. Well, how do you add 1? What's my exponent? If it's not written, it's 1, right? So add 1 to it, it becomes 2 divided by 2. Okay, and then 0 and 1. So what? I put 1 in here and 0 in there? No. You put 1 in everything and 0 in everything and then subtract. Let's do that. So it is 1 minus 1 squared over 2. You can do that, right? Minus, and now I plug in 0. 0 minus 0 squared over 2. Now, the back is all 0, so what we're left with 1 minus a half. Exactly a half. So, whatever they told you in high school or kindergarten, whatever it is that you learned, it was correct. By the way, we also know the area of a circle, but to find the area of a circle using calculus, it's much trickier. Because it's an integral that is not so easy to calculate anymore. In fact, at the moment, you don't have the tools for it. So when we have it, I will show you how to do it, okay? Okay, so now I should perhaps explain the formula, right? So I remind you, we have this function f. Now, we know it's an area with sign, so it could be that f goes underneath the curve, but for the picture, I'm going to keep it simple. I'm going to keep my f above it, but it really doesn't matter. And then we have that f is an antiderivative, okay? Now, what is that I have to calculate? What I want to calculate is this green part. Oh, that was with this guy, this green part here, right? The total area underneath this curve, okay? Okay, and how did we do that? That was using these Riemann sums. But that's was not very helpful at all. So I'm going to think about it a little bit differently. I'm saying, okay, what if I think of this not as why don't I do this little by little? Instead of calculating from A to B, let's go like perhaps halfway only. In other words, what I'm thinking about is, think of green as a curtain, okay? And in the initial setup, we are here. No curtain, right? The curtain is open. There's nothing. You take the stage and it's all open. But now I'm going to pull the curtain little by little from A. I always start from A. So suppose at time t I've gotten this far with my curtain. So this means what now? I have here my curtain, right? Yeah, this is my curtain. So this I already calculated. So write down what this is. So the green, the green thing, yeah, okay, that was green there. Perhaps I should, let me take a different color. I don't want to confuse you. So I'm going to take a different color. I do orange. Who doesn't like orange, right? Here we go. So the orange thing, what is that given? That's a formula, right? I have a formula for that. That is from A to, this t here is a moment in time, if you want, between A and B. It's a point between A and B, so that's t here. And then the function is still f, so f of x dx. Okay? That's the orange guy. And a little bit later, instead of t, I might be a little bit later, so I'll do that here. Is my t a little bit later, so t plus h. H is a little bit further. So what does it look like now? I'll do this in blue. So now I would have this guy, right? So the blue guy is... Well, what's the blue guy? Before I do that, write down the formula. I can write down the formula, but I'm gonna... This depends on t, right? Because I'm moving my t around, so I'm thinking of this as a function of t. It's a clever thing, right? Mathematicians often do that. If they have to calculate numbers many times, they say instead of calculating for each number separately, I'll make a function out of it. And then once I have the function, I just have to plug in. So I'm going to call this g of t. G of t is the area at any given point t. So t is here, or t might be there, or it might be a bit further, or perhaps even all the way at the end. That is, the g of t represents the area that of the curtain so far being pulled out. Understand what it is? Okay. So in the first case, it was the orange guy. In the blue case, so what is the blue case now? Well, that is g, but now we have gone to t plus h. Okay? Good. You following me so far, I hope? And if you don't, go back and then see what I'm saying. Now I'm going to do something. I'm going to look at this difference here. Why I do this? Because it works. That's the only thing I can say. I'm going to look at this difference. What is this? That is the blue, that is not orange. In other words, we're talking about, let's make it purple, we're talking about this guy here, right? And okay, there's curvature here, but I'm going to flatten this. So it's not exactly even because I flattened, right? You see, the curvature I've flattened, but I can therefore say what it's almost equal to. What is it almost equal to? Well, it's almost equal to this height, f of t, times this width. What was the width? H, right? ft times h. I've done so often now, worked with these strips and flattened them, and these are just rectangles, and the area of this rectangle, so this purple thing, that's the difference between the blue and the orange, right? At least almost, that's why the twiggly. Why is it almost? Because I flattened, right? The real actual thing would be has this curve on top, which it's hard to see, but it's there, right? Okay, so we have this. You agree with me that this is at least almost equal? Okay, and again, almost gets better and better if we make the quantity smaller and smaller. In this case, h. Don't forget it. Now, that's the first thing I did. The first manipulation. Next manipulation is I'm going to divide both sides by h. Why not? We can do something with it. Okay, gt plus h minus gt divided by h. The whole thing by h, so write it as a big fraction, is approximately equal to f of t. Now, I don't like that. I don't like approximately. I want to get back to really equal, and we discussed this. If I make the strip smaller and smaller, in other words, if I make the difference between one moment and a little bit later, in the way that I'm pulling open my curtain, then the arrow will be smaller and smaller. And therefore, so the smaller, let me write it up, the smaller h, the smaller h, the better my almost equal to, right? Okay, that means in the limit, it will be gone. It's now actually equal. That's the trickery with limits. Good. What does that now do to me? Hey, Professor, I've seen this thing. Where did I see this? It was not in this course. Ah, it was in Calc 1. What is this? This is the limit of a difference quotient. And what does it represent? The derivative of what? Of g. So this is the derivative of g, of the function g. The variable is now t here, right? Huh. This says that the derivative of g is f, but I can better say this. This means that g is the antiderivative of f. Right? This is kind of, the derivative of g is f, so the antiderivative of f is g, right? It's turning things the other way around. Ah, that's the antiderivative. Okay, good. So what is this? Oh, one thing, this is what we call the other part of Fundamental Theorem of Calculus. It shows that, in fact, the function f has an antiderivative, namely g. The function g is defined, right? We define it as the area at any given moment as I'm pulling out the curtain. And, okay, I didn't state that, but the limits, these Riemann sums, always exist. That's actually Riemann proved that. And therefore, these areas always exist. We talk about that. We always assume that these things are working. And it's only in cases where you don't have continuity and so on that things can go bad. But here it always exists, so g exists, and this tells me that g is the antiderivative of f. So f has an antiderivative. So every continuous function on an interval has an antiderivative. That's not obvious at all, in particular, because many times we won't be able to write down what the antiderivative is. We had all these formulas, beautiful formulas, sometimes very complicated to find derivatives functions. So in principle, we could find the derivative of any function. But the antiderivative of a function, that's a whole other story, as we'll see. But that's not the issue now. Okay, so this is where I am. But wait, I was starting with something. I had already an antiderivative, capital F. Remember in the theorem, when we were given the Fundamental Theorem of Calculus, this f was the antiderivative, was given to us. We had because we can calculate it often, right? So here, with this one, we would have calculated the f. So that means that f and this f and g are the same, because they're both antiderivatives? No, because there might be, what's the difference sometimes? There's not just one antiderivative, but every other antiderivative is true up to a constant. So what we can say is that up to a constant, they are equal. Oh, sorry, that's not what I want to do. So there is a c, so for some constant c, we have this formula, this equality between the two. Okay, all right. Now let's calculate actually. Sorry, can I write? I wrote a plus c here. Oh, I don't know why I was trying to do that. I wanted to write a plus c here. Okay, it doesn't matter where I write a plus c because it's a constant, could be anything. If I write it on one side and I want to bring it on the other side, you just take the negative, and that's again a constant. Okay, so that's what we are. So let's look at this quantity here. No, sorry. No, okay, let's look at the quantity, the formula. Let's do it this way. The formula says this is what you have to calculate. This is going to give you your area. Okay. So FB minus F of A. Okay. Now F is given by G plus C. So G plus C, you plug in B. If I plug in B in G like that, what will happen if I plug in B in C? Well, C is a constant, doesn't change. Okay, so GB plus C minus, and now I plug in A, right, and subtract. So GA, again, that's just a constant. Ah, that's nice, the constants cancel. We get GB minus GA. Okay. So what is GB? What is GB? Let's go back what G was. G was the function at any given time of my curtain. So what was this GB then? Yeah, but wait a sec, this is GB, the green guy, right? The green guy is GB because that's the whole curtain. That's when T is when I did my complete movement, that T went all the way to B. So this is actually what I want. So actually this guy is the one I wanted. That's my area. Oh dear, there's a GA here. What is that then? What is GA? Oh, but what is GA? This means my T, let's go look at the picture, mess with the picture here. This would mean everything here is gone, right? There's no T here yet. I haven't started yet. In other words, here's my function. I haven't started yet. So this is G of T. What's the area of a line? Nothing, right? It's a one-dimensional thing. It has no area. So this is G of A. Sorry, G of A is nothing yet. So G of A is 0. Ah, okay, so this is 0. So this is GB, which is just the area. Huh. The area, that what I wanted, is FB minus FA. That's exactly what this fundamental theorem of calculus says. The area, remember, is given by this integral, right? That's why that's the link between these two integrals, because it now explains, right? In order to calculate different integral with endpoints, you do the one without endpoints, and then you put in the endpoints, basically. Okay, so a lot of homeworks to practice this. I'm going to go quickly over this. This is in one session. I covered a couple of sessions from the Calculus 1, but it is a review. Okay, and then tomorrow we're going to start already with our integration technique. So this is a base. You have to have this base ready, especially the homework problems and the derivatives and definite integrals and so on. So make sure that you're ready for the next one.